It was estimated that 40% of drivers in Oregon talk or text on a cell phone while driving. Since that estimate was produced, the number of young drivers in the state has increased, and also a new law was enacted this year for a higher fine if caught using any type of electronic device. Has there been a change in the cell phone use since the last estimate was taken? A study is conducted and a random sample of 33,645 drivers are taken by means of photographing randomly chosen road locations at random times of the day. Of the drivers observed in the photographs, 1,512 were observed using an electronic device while driving. Let's conduct this test. What's my null hypothesis? This is quoted to me as an estimate, but we have no other estimate. This is the best we have. So we have to assume that this is still, we don't know. Again, this is where we keep mentioning that null hypothesis is an assumption. How we come to arrive at this assumption depends on the situation. There's many different ways of why we arrive at this value, but we're playing a game of what if. What if this is really correct? So my alternative is going to be, this is not correct. But now we have to determine in what way is this not correct. So these values get repeated over again. The population parameter, in this case, population proportion, and what are we assuming is the correct population parameter value. What is it the study is trying to say? Well, here it says there's some laws been enacted, and we're asked, has there been a change in the cell phone use since the last estimate was taken? A change doesn't imply any direction. Maybe the law has caused this value to go up. Maybe the law has caused this value to go down. Maybe it's remained completely unchanged. The law hasn't done anything. But a change doesn't imply direction, so this is going to be a two-sided test. What's my statistic? Well, the statistic has to come from a sample. In this case, again, it's p-hat, the estimate of population proportion. And it looks like we had a sample of 3,645 drivers. And 1,512 were used observing electronic devices. That's my statistic. Notice there's a difference between statistic and test statistic. Make sure you remember the difference between. The statistic is the estimate of my population. The test statistic is a standardized measurement. Okay, so this is the standardized version. What's my effect size? The difference between these two, I'm going to just write here an estimate of this. I'm not going to write one down. So the effect's at approximately. So noted, the effect size actually is small. There's about a little about a 1.5% difference between what I observed and what I expected. And I see that it did go up a bit from the statistic here, from what it was before. Now let's calculate my test statistic, which is going to be the z-score. It's a little too tight. Notice it's probability of success, probability of failure. These have to add up to 1. And this is approximately, let's come over here, 15, 12, 645, 645, and I get my value 1.825. And I'm around. Okay. Can I use a normal approximation? Well, I mean, the sample size is huge, but again, I need to do this calculation, and I can see that this is very close to 50%. So yes, I can visually inspect, and it meets, again, this criteria, n times p is greater than 10 easily. And also, actually, I should be using 0.4, not this. You're not using my statistics, you're using the parameter in this case. So it looks like above I also used the statistic. That I should have used a parameter here as well. Later, we'll have to use a statistic, but right now we need to use what we think is correct, which is a 0.4. So I should have used 0.4 here. So it should have been 0.6. So use what you think is correct. This is just an estimate. You use this only if there's no choice, like you don't know what this is at all. But we're assuming we know what this is. So 0.4 here, 0.6. Both of these are greater than 10, not a problem. Don't even need to calculate. So yes, the answer is yes. Can I use a normal approximation? Yes. Again, central limit theorem. So this allows me to draw this picture, which again, I've been recommending you do this all the time. I still see people not doing this. I do it because it allows me to think through the problem. And here's my p-hat value, specific. And now the question becomes, this is a two-sided test. How's this going to work? Which direction do I go? Here's what I observe. Which direction am I going? In a two-sided test, you need to go away from this. If I had landed on this side, I'm going to go in this direction. So I'm going to go in this direction, right here, away from this. This is directionless. If I was in the other one, in the one-sided, so one-sided test, I go in a direction that this is telling me to go, less than. I landed here, less than. This is directionless. This is a two-sided test that we're conducting because we have a not equal to, so this is going to be a two-sided test. In that case, I go away, just away. I land on this side, away. And this is not the p-value. But we still need to calculate it. But that is not the p-value. But let's calculate it anyway. So I come over here, p-hat greater than 0.4148 approximately. This turns into a z-score. That's approximately greater than 1.825742. Great. And now enter this into GeoGebra. Go to the right, click to the right, and enter 1.8525742. 0.0339, again, so approximate to 4 decimal places. This is the chance of observing 0.418 in statistics, if this is correct, or even more extreme, but that's not the p-value. What is the p-value? And the p-value, what we're saying is, this is my effect size. And we want to calculate, so the distance between here and here, the effect size is 0.0, I'm looking up here, 0.0148, that difference. But a two-sided test says, what's the chance of observing an effect size as large as this, or even larger, if this is correct? But this is directionless, so it has to be on either side. So the p-value is a result of summing these two sides up. Obviously, you only land on one side. So the p-value, in this case, it's going to be 2 times twice 0.0039. What is this value? 0.0678. And that's my p-value. So what does this mean? Just like what I said a second ago. If the population parameter equals 40%, for again, the situation, I would write it rather than words, but there's not a lot of room here. So if is correct, this is very important to state. You need to state how you started this. You started with this assumption, and this is, you're starting with this assumption. If this is correct, the probability of seeing an effect size of 0.0148 or greater is 0. And I'm going to put this here just to make sure it's clear, or greater in either direction. Of the mean. is 6.78% from a sample. I think actually you should always quote the sample size too, from a sample of, because that does matter, 3,645 drivers. So the 40% applies to the number of drivers that talk or text on a cell phone while driving. So at any given instance, that's a lot. What can I infer? Has the law changed behavior? Basically, what I'm asking you is 6.78% rare enough. Now, you don't have any sense of how to interpret this, so but we're going to do that next. But the answer is, well, 6.78% is unusual. For most people, it is not enough to conclude K equals 0.4 is not correct. Notice we're using a lot of double negatives. It's just part of the language. And part of that is because we cannot say this is correct. What we're saying is if we assume it is correct, then we don't have enough evidence to conclude 0.4 is not correct. Okay? So at the moment, continue to assume it is correct. So we deal with a lot of negatives, double negative, even triple negatives in statistics, just due to the logic of what we're trying to do.